So now that we've defined these function spaces, we can start to talk about differential operators. So here's a slight recap of what we did in the previous video. And we're talking about the H1 Sobolev space, and we defined this to be a set of functions, and specifically sets of functions in L2, but with another requirement, namely that its H1 norm is well defined, is non-infinite. And the way that we then defined this H1 norm was a Hilbert space, which meant that the norm was defined by an inner product. So we defined the H1 norm of a function u squared to be the inner product of u with itself, u with u. And the H1 inner product was defined as the L2 inner product of the function plus the L2 inner product of the gradient of the function. And the L2 inner product of two functions was the multiplicand of those two functions integrated over the domain. An important thing to realize here is that now with this class of functions defined, we have a class of functions for which we know that we can take the first derivative. We know that we can take the first derivative, and by doing so, we still have a well-defined operation, right? We don't get any infinite values there. So that gives us the opportunity to start talking about differential operators. And differential operators, the way that we are usually taught them, is by taking a small difference of a function from a point x and x plus dx, and then take the difference between the function of those two positions and divide by the length. That's what we get taught in calculus. This, however, gives us a slightly different interpretation of differential operators. Now, differential operators become mappings between function spaces. And of course, these are equivalent operations in a sense. And if you would actually want to perform a differential or have a differential operator act on a function, then you would have to go back to calculus. But from a conceptual perspective, we can now talk about differential operators as being mappings from one function space to another. So for instance, a differential operator in 1D, that is simply dx, is going to be the mapping from H1 omega, the set of functions for which we're at least allowed to take one derivative, maybe more, right? So H2 is also inside of H1 and H3 is inside of H1. And these functions are somehow mapped to the function space L2, the function space where we don't have any requirements on the derivatives. We've taken the first derivative from the function in H1, which means that we can't say anything about the regularity of these functions anymore. So at the very least, they have to be in L2. So that's now how we're going to interpret this differential operator as a mapping from one set, which is a Sobolev space, to another set, which might also be a Sobolev space. And in general, we would say we're taking a Sobolev space of order L, and we end up in a Sobolev space H0, which is actually precisely L2. Yeah, so that's a Sobolev space with zero requirements on derivatives, and that's going to be L2. So in general, we'll write a differential operator for which I have the symbol L to be a mapping from HL to H0. And now this is an Lth order differential operator. So that's about the operator. What about a differential equation? So now a differential equation. Well, taking use of this symbol curly L, we would write a differential equation as curly L acting on a function phi such that this produces our data f, our given function f. Or let me actually stick with u for now. I think that's the symbol that I've used most often. U of x. So then, if L is a second order differential operator, such as the Laplace operator, then we're going to interpret this differential equation as the mapping L from H2 omega to L2 of omega, where we're given some function f in that very unrestricted function space L2. This can be almost any kind of function that you could think of, irregular, regular, discontinuous. So we're given some function in f, and then we're looking for the function u in H2. That's the question that we're asking ourselves when we're posing a differential equation. Differential operator acting on some unknown function is going to give us some known function. So now what is my unknown function? So I'm looking for the inverse mapping of L. So if we think of it like this, much rather than taking a differential difference and dividing by that, then we understand that a differential operator is really about the question of does an inverse mapping of L exist? So that means that for every point in our output, the image of L, the codomain, if there's one and only one solution in the domain of L that maps to that output. Now this is still from the perspective of mappings, right? And we're calling this a branch of mathematics functional analysis. So somehow it's still going to change this to make this look like these functionals much rather than these mappings. But I hope that you kind of appreciate that this is a slightly different perspective on this. Now this is still what we're calling the strong form of our equation. This is the strong form. And here you can think of the strong form as the form where we have these actual mappings. And in the end, what that's going to be about, it's going to be about the 2 in our sublet space. That if we have a second order differential operator, that we need our functions to be twice differentiable. And that seems very obvious, but we'll see in a second that if we actually have a slightly different form of our differential equation, then this is actually not necessary anymore. And that's going to give us some benefits. Okay, so this is the strong form. Now let's move to the functional form. So, how do we obtain a functional form of our differential equation? Well, there's many different ways in which we could obtain a functional form of a differential equation. I think one of the most robust approaches is with the method of weighted residuals. So what we're going to say is, well, we have this differential equation where a differential operator acting on my function u is going to be f, and f is going to be in L2, which means that my differential operator acting on u has to be in L2. So I'm going to move my left-hand side to the right-hand side, and this I'll define to be my residual. So now I'll define the residual r to be equal to my data f, which is a function in L2, minus L acting on u. That's the residual. Yeah, and given that our data is in L2 and given that this differential equation is stated as LU being equal to our data, we know that the residual is actually also some kind of function in L2. So now clearly we're looking for the function u of x such that our residual is equal to 0. So now we can state our equation in a slightly different way. So our strong form would still be equal to our residual is equal to 0. But rather than stating that the residual is equal to 0, what we're going to do is we're going to test our residual against other functions. And specifically what we're going to do is we're going to say that the residual is equal to 0 is going to be equivalent to taking the L2 inner product between our residual and some weighting function that is going to be equal to 0 for all weighting functions in L2. Now I'm allowed to carry out this operation. These are the kind of things that you can start thinking about if you write your equations like this. I'm allowed to perform this operation because R is in L2 and W is in L2. So naturally I'm allowed to write the L2 inner product between R and W. So far I've actually not changed quite a bit. Now what does this really mean? This means that I have this residual, which is somehow a function L2, which I want to be 0. So what I'll do is I'll multiply this by W. So suppose that we take W to be a function that really just looks like this. It's going to be 0 almost everywhere, and then it's going to have this non-zero value, and it's going to be 0 everywhere else again. So if I multiply by that, I integrate over a domain, and then essentially I'm sampling my residual at this location, right? So if I now can say that this multiplication is going to be and integration is going to be equal to 0 for all choices W, then I can essentially create infinite choices of these samplings. And if they're all equal to 0, then, well, we found that the residual is equal to 0. Now, it turns out that we can actually relax our statement a little bit. So this actually is a function in L2, right? This is a function in L2. I can square this function and integrate it, and it's going to give me a perfectly fine value. But I can relax my requirements on my test function a little bit. And what I can do instead is I can also test this for functions in H1. What I can do rather than making this discontinuous function is I can just make it continuous. And I can sample my residual with functions that look like that. So now I've changed my weak statement a little bit, and I'm going to say that I want my... I'll start using these inner product notations now, because in the end you have to write this so often that writing the integration symbol is going to be a bit tedious. So what we're going to change this notation now a little bit. We're going to say that the residual weighted by W in the L2 inner product sense is going to be equal to 0 for all W, but now not in L2, but rather in H1. And that's still going to be an equivalent statement. So far I haven't really done much yet. But now I can carry out a certain trick, and I'll show this with a practical example, right? So I'll move away from my my general notion of a residual here, and I'll specify my differential operator. So now I'm going to say, suppose that my differential operator is equal to, well, let's take the example of the advection diffusion equation. So then we have a differential operator that was A dot the gradient minus kappa times the Laplace operator. Right, that's where our function would go. Which means that the residual is equal to f minus A dot gradient of u minus kappa times Laplace operator on u. Okay, now let me substitute that in our statement. So what we're really looking for is what we're really saying is find my solution u, which at this point is still, according to our strong form, but we'll get back to that in a second, is some element of H2. So find my solution u, which is a member of H2, such that the integrand over omega of f times w minus a dot gradient times gradient of u times w minus kappa times Laplace on u times w, and that is going to be equal to 0 for all w in H1. So what I can do right now is this, well, this is a perfectly well-defined integral, but I can do an integration by parts here. So let's carry that out. Let's rewrite this a little bit, and I'll actually also move my data to the right-hand side, right? That's what we're used to. And lastly, I'll multiply the whole thing by -1. And this should be a plus, sorry. The residual, check. Yeah. Okay, so if we do all of that, then what I'll get is the integral, and I'll leave some space, and we'll see in a second for why that is. The integral of, and I'll start with this term, a dot gradient of u times w plus another integral over omega of kappa times the gradient of u times the gradient of w. I've done integration by parts. So this is actually the kind of derivation that I hope that all of you are familiar with. And if you're not, then you should really look into that, because I'm not going to go into too much depth of how I go from this statement above here to the one below. But I still need one more term for that. It's equal to partial omega of kappa gradient of u dot n times w. And that's going to be equal to integral over the volume of f times w. And that still needs to hold for all w in H1. So now we see why we needed this regularization. We had all these functions in L2 against which we were testing. And then we said, well, we're going to test against fewer functions. We're going to test against functions in H1. There are fewer of those, but they have more regularity. And now we see that we actually need that to make this statement, because we have now a gradient of w as well. And this would only be defined for functions in H1, and it would not be defined for all functions in L2. So then it would become an ill-posed statement. But now that I've said my test functions live in H1, I'm allowed to do this. So for this statement, I still needed my solution to lie in H2, right? Because I want to take two derivatives here. In this statement, I no longer need this. I only have first derivatives of u. So I can actually loosen my restriction on u a little bit, and I can change this. Now we're going to change it. This is no longer an equivalent statement, this is a new statement, to say find u in H1 omega such that this statement holds for all our test functions. So now we have released some requirements on our solution. It no longer needs to be twice differentiable, it needs to be only once differentiable. Now, and if this is the first time you see stuff like this, then it always feels very strange, and that is because we are so trained to think about this strong form. But I guess the point that I would like you to start realizing is that this is in many ways the more appropriate way. In many cases, specifically in solid mechanics, we actually come from a minimization of an energy, and then you come from these kind of statements, you come from these integral statements. So then the natural perspective is H1, and only via moving this to a strong form do we find that we need to be more restrictive. But our underlying physics is based on this statement. So we should be looking for solutions that have fewer regularity requirements and are only in H1, not in H2. And to give another argument that I don't specify too much, I won't specify too much, is that you can actually prove that this is now a complete collection of all solutions for all possible data. And in the original strong form, you can't do that. So in the original strong form, there is actually missing solutions for particular choices of data. And with data, I now mean not only f, but also your boundary values. Yeah, so I'm not 100% correct here. I should still treat this term. I should put for instance, Neumann data here. Or I should kill the test function on the boundary being 0 on the Dirichlet boundary. And then we have Neumann data, we have Dirichlet data, and we have this F, the forcing data. And only in this weak sense can we get a full collection of results for all this possible data. Yeah, so this is really the more appropriate way of looking at partial differential equations, even though we are very, very used to thinking of them in a strong form. Yeah, this is the more complete form. And the last thing that I would like you to see right now is that these are actually functional. So this is a functional form. But actually to make the point that I just made very explicit, so now we're dealing with a weak form. And weak does not mean poor, it actually means better. It's better than the strong form. The weak form is better than the strong form, and it's because the strong form is too restrictive and the weak form is just not restrictive enough. Okay, so now these are actually functional forms, because what we can see right here is that the operations that we're performing right here, and well, actually I'll go until here, because in the end this red underlined box would move to the right hand side. If I substitute my data there, then the U is eliminated and it can go to the right hand side. So what I just underlined, what you see is, well, that is some sort of an operation that takes a function u and a function w, and if I give it a function u and a function w, then it will give me a number, right? So it's a functional. Actually it's a bilinear functional. So this I'll write as b of u and w. Yeah, and that's going to be a mapping from H1, our space for u of omega, and it's bilinear, so we have to write this cross product here, and another space H1, our space of test functions, and it's going to map to the real numbers. Now it's going to give me any number for any one of these functions in any one of these two spaces. And it's linear in the sense that if I multiply u by 2, then I'll get twice the result, same for w, and I can add two functions in H1, u and v, and bilinear form would decompose in the same way, right? So it satisfies all the requirements for linearity that we defined in our previous lectures. In the same way, all the right-hand side is going to be only dependent on w, right? So we have f times w. So this is a linear form, in the sense that it's a mapping from H1, our space for w, and it will also produce a real value. So now again, the general way that we would write our weak formulation is by saying that we're looking for our solution u, which is a function that lies in the H1 subleft space, such that the equality bilinear form u w is going to be equal to the linear form on w for all choices of test function w in H1. And this is the statement that we'll use as our point of departure for analysis. And that's something that I'll do in a three-part video. But before we go into that, I actually want to make one more video that's going to be specifically about the boundary conditions. I've been a little bit unspecific here, so I want to actually address one point in terms of Dirichlet boundary conditions. Okay, that's it. Thank you.